Very good morning to all of you, my dear students. And today's menu is the application, the last application of the Goldras law, the ionic mobility, the difference between the ionic mobility and the ionic velocity, calculation of ionic mobility, then transport number and its determination. Next one is the Defecal-Onsager equation. I'm sorry, the conductometric titrations. Here, no much problem is so far asked, but graphical representation of various types of conductometric titrations that can be asked, that can be easily tackled. Then finally, the Defecal limiting law. That is a law limiting, why it is called limiting law. What are the problems that can be asked from that one? This is today's menu. With this menu card, I'm going to start the last application of the Goldras law. The third application of the Goldras law is the degree of ionization of a weak electrolyte. The degree of ionization of weak electrolyte can be calculated using these conductivities, using the conductivity measurements. The degree of ionization, the alpha is given by the lambda that is equivalent given concentration. Lambda C is that a given concentration divided by the lambda at infinite dilution or at zero concentration. This will give you the degree of dissociation at the concentration C. That can be easily calculated, and for which we are going to derive this equation. We have already represented for the weak electrolyte one graphical representation, a straight line one. And at that time, I told you that I am not going to derive the equation, how this equation arrived at, but situation arises that I have to derive that equation. You are making use of this derivation. An important question in the CSR question may be, examination may be asked. So far, such a question is not asked. If at all asked, how to give the answer for this? Therefore, first I am going to derive the relationship between the lambda 0 at infinite dilution and the lambda at a particular concentration, for which you should well know about this. The phosphorus dilution law for a monobasic acid. You know what is a monobasic acid? That is releasing only one H plus ion is called the monobasic acid. And the same explanation may be extended to monoacidic base also. Therefore, this application is degree of ionization for weak electrolyte. That weak electrolyte may be a weak acid or a weak base. I'm going to give the phosphorus dilution law. You know, at a particular concentration, a small amount of HA would be ionized as H plus, and it is excess the hydronium ion. And there will be equilibrium between the ionized molecule and the ionized ions. Now let us take initial concentration of the unionized molecule H as 1, and the ionization at the initial condition is 0, 0. Then it is dissolved in water. Ionization takes place to a small extent. Let the degree of ionization, we call it as the alpha. Therefore, at the equilibrium, how much amount of the unionized molecule would be there? 1 minus alpha would be there. How much amount alpha moles and A minus alpha moles. This is the concentration when we take the initial concentration as the 1 mole. If you take the initial concentration as a C mole, then you multiply whole things by C alpha and C alpha. Then what is the equilibrium constant? Here the equilibrium constant is given called the acid ionization constant or acid dissociation constant. It is given by the concentration of the product C alpha into C alpha into the by divided by the concentration of the reactant C into 1 minus alpha. And in the concentration of water, here the generally the K value equilibrium constant is given in terms of, I have already told you, given in terms of the activity of the products divided by the activity of the reactants. Activity is equal to the activity coefficient into the concentration, into the molarity or molality. And for a very weak solution, the gamma value, that is activity coefficient, is taken to be unity. Therefore, now K is given instead of the activity, we are giving in terms of the concentration. Therefore, we are giving the concentration unit, and you get actual equation is C alpha square, C square by C alpha square, C1 minus alpha. If you cancel this, you will get C alpha square by 1 minus alpha. This is Ka. Generally, to simplify this equation, we assume the alpha is beta 2. Therefore, Ka is taken to be equivalent to C alpha square. Therefore, if you calculate alpha, and if you know the concentration of the weak electrolyte, you can calculate Ka. Therefore, this relationship you should have bear it in mind. Alpha is given by the equivalent conductance at the given concentration by the equivalent conductance at infinite dilution. And another thing, what is the concentration of H plus ion? They may be asking you. The concentration of H plus ion is nothing but C alpha. And sometimes the H plus ion, if you know the H plus ion concentration, you can calculate pH of the solution. Therefore, giving this, the alpha and the H plus ion, giving this and the C, you may be asked to calculate the pH of the solution, and this is the methodology by which you can calculate this one. And another thing you can, the same thing can be extended to the base. In such cases, instead of A, you have to put Kb. Therefore, Kb. Here, instead of H plus, you put in the OH minus. OH minus is equal to C alpha. Knowing OH concentration, you can calculate POH. Knowing POH, you can calculate pH. Therefore, in the case of OH minus concentration, basic is given. They give the equivalent conductance at a given concentration and equivalent conductance at infinite dilution, and the concentration of the base taken. You are asked to calculate pH of the solution, for which you should calculate the OH concentration, convert into POH, then convert into pH. 3 steps should be there. But the methodology is the same things. And I'm going to derive the relationship between lambda and lambda not for the weak electrolyte. And from this is a side one. If at all you asked to calculate this one, how to proceed like this. Now I am going to relate the lambda C versus the lambda naught using this equation. What is the equation? We have derived an equation for the Ka. The Ka is equal to C alpha square by 1 minus alpha. Here we are not going to omit the alpha value. We are going to take this. You know, alpha is equal to lambda C by lambda naught. Okay, put the value of the lambda. I'm sorry. Here you will get what you would be getting. Ka is equal to, or we can rearrange this. It is Ka. Ka is equal to C concentration into alpha square lambda square by lambda naught square divided by 1 minus alpha. Alpha is nothing but lambda C by lambda naught. Bring this value in this side, you will get Ka is equal to 1 Ka into 1 minus lambda by lambda naught is equal to lambda square by lambda naught square. Or bring this lambda naught square in the other side, you will get Ka into lambda naught square into lambda naught by lambda square. Lambda naught is equal to C lambda square. Or you cancel this and this, you will be having this much one. What is the relationship? You will be finally getting Ka into lambda naught square minus Ka into lambda naught into lambda is equal to C lambda square. Here, Ka is a constant for a given electrolyte. Lambda naught for that electrolyte is a constant. Therefore, it is a constant. Let it the constant be C. Ka is a constant. Lambda naught is a constant. Let it have the M. The A is going to vary. I'm sorry, lambda. The lambda is going to vary as C varies. And the C lambda square is equal to Y. Therefore, it is in the form of Y is equal to C minus Mx. If you plot Y versus X, you will get a straight line with a negative slope. And using this equation, one question may be asked. Take down the question, and now you are ready to give answer for this question. Take down the question. The dissociation constant K within bracket would K of a monobasic acid is determined conductometrically. Then, which of the following statements are correct? Which of the following statements are correct? A. A plot of C lambda square versus lambda gives a straight line with a positive slope equals to K into lambda naught, and a intercept equals to K into lambda naught square. Or simply I will put it in another way. What is the plot and the nature of the curve? Slope equals to, next, intercept equals to. This is what they are putting. A plot is between C lambda square versus lambda straight line, positive slope, which is equal to K into lambda naught, with the intercept equal to K into lambda naught square. Just now we have derived on equation. What is the equation we have derived? K lambda naught square minus K lambda naught into lambda is equal to C lambda squared. Now I have told you that this is a constant and this is a constant, this is a variable and this is a variable. It is in the form of y, it is in the form of x, it is in the form of m, and it is the form of this. I have derived this one. From this, when in the y-axis CA square, C lambda square is taken, and the x-axis lambda is taken, you should get a straight line. But a slope is a negative, and the slope is equal to k into lambda naught. And the intercept is equal to k lambda naught square. This is correct, this is correct, this is correct, this is correct, but this is wrong. This is a one option. Second option, a plot of CA, C lambda versus 1 by lambda gives a straight line, with negative slope, equals to minus k into lambda naught square, and the intercept equal to minus k into lambda naught. Here they have slightly changed this equation. How they have changed this equation? Ca versus 1 by lambda and C lambda by 1 lambda. How they have changed this one? C lambda by 1 lambda. You just divide this equation on both sides by lambda. Now the equation would be k into lambda naught by lambda minus k into lambda naught. This lambda gets cancelled, is equal to C lambda. Now if you take this y-axis, this is a constant C minus this Ka, this is a constant M, 1 by lambda is a variable. That is, it is Ex. Therefore, now you plot this 1 by lambda is the x value, plot y in the C lambda in the y-axis and 1 by lambda in the x-axis. Once again, you will get here, this is what they have given. It is a straight line. Slope is a positive, but it is given as negative and equals to Ka lambda square, but it is given minus the wrong. And intercept with the minus K lambda. Okay, this is correct, but these two are wrong. Therefore, B is not correct. Next is C. A plot of C lambda square versus lambda gives a straight line, okay, with a negative slope, equals to minus K lambda naught equals to minus K lambda naught, and intercepts equals to K lambda naught square. Look at the first equation and find out whether it's a correct or wrong. Straight line correct, and it is a minus mx, is not? Therefore, it is negative, and in m is equal to Ka naught. This is also correct. Intercept is also correct. Therefore, this is a correct statement. And D option. A plot of C lambda versus 1 by lambda gives a straight line with a positive slope equals to k lambda naught square and intercept equal to minus k lambda naught. Now they have taken the second equation, whether it is correct or not. When you plot c lambda versus 1 by lambda, and if y is equal to mx minus c, a straight line, okay. And you will get a positive slope, okay. And the slope is equal to k lambda naught square, okay. And intercept is equal to, this is the intercept minus k lambda, therefore C and D. Then take down this one. Option B are correct. Option B, C are correct. Option C, D are correct. Option D, A, D are correct. It is the correct answer. And this type of problem so far not asked in the examination. But if it is possible, you, whether you have to derive this equation in the examination hall, or you can keep it in your memory and immediately you can give the answer for this. If at all this type of question is asked, it will be asked in the part C. Okay, next we will see the next type of possible problems. Take down the next type of problems from easy level 2. We will be moving towards, yeah. Your voice is not audible to me. I am going to write it once again. What is answer in this? See, first equation is k lambda naught square minus k into lambda naught into lambda is equal to c lambda square. This is the first equation. The second equation is divide the whole equation by lambda. You will get k lambda naught square divided by lambda minus k lambda naught. This is what you ask. Am I correct? Alpha is equal to lambda by lambda naught. Yeah. Alpha, yeah, Ka is equal to C square, C alpha square by 1 minus alpha. Yeah, assuming to make the problem, to make the solving the problem easier, we assume that alpha is very, very small compared to 1. Say it may be 0.04. Therefore, the remaining is 0.96. It may be taken according to our approximation, we will take it as 1. Therefore, alpha can be neglected in comparison with 1. They will do this. But in this problem, they have included the alpha and we have worked out this. Sometimes if you are asked, cancel this and Ka is equal to C alpha square, now your equation will be something different. You in your home work out, if you assume alpha is negligibly small, what would be the relationship between lambda and lambda naught and lambda, and how the equation would be there, and at that time what would be the slope, what would be the intercept. You can easily work out. Next, with this next doubt. Assumption, if it is given in the solving the problems, you assume alpha is negligibly small, or what is the percentage alpha value you have calculated is 0.03, etc. You can assume that it is very low compared to 1. When any value can be neglected, the value should be compared. By comparison means, what is the method? The value, if suppose a minus alpha or a plus alpha, when it is comparing with either with the minus sign or with the plus sign, You can easily neglect this. Alpha is small compared to this. Therefore, whenever you subtract alpha from A, the remaining would be equivalent to A. Or whenever you add alpha to this, when it is equal to A. But A divided by alpha, when these two are related, it's just like this in the divisor. You can't neglect the alpha. You can't say it is very small, therefore I am going to neglect in comparison with the alpha. You can do the neglection of the alpha. Only it is either in the negative or in the positive sign with the nearby parameter, or whenever it is in the division or it is in the multiplication, A into alpha, you should not neglect the alpha values. Next it out. Okay, we will go for the next type of problem. Take down the next type of problem. The equivalent of KCl at point 1 normal, point 1 normal is 130 per room centimeter square per equivalent, and lambda naught 150 per room centimeters equivalent. The degree of ionization of potassium chloride is the degree of ionization of potassium chloride. It is very simple. You can easily work out. The degree of ionization is given by the formula. Degree of ionization is given by the formula. Alpha is equal to lambda by lambda naught. Lambda is 130. Lambda naught is 150. Therefore, you can easily calculate this one. And we will go for a little bit difficult, increase the difficulty level. Take down the question. The lambda naught of acetic acid, here we are going to give for the weak electrolyte at 300 degree Kelvin is 400 per row centimeter square per equivalent at a concentration of 0.001 normal. 0.001 normal. Compute lambda C, that is equivalent concentration, equivalent conductance at a given concentration C. If the degree of dissociation of the electrolyte is 4.2%, the degree of dissociation of the electrolyte is 4.2%. This problem is just a reverse of the previous problem. But the next I'm going to give is the somewhat difficult. Somewhat, no, it is not difficult. You know the relationship, just you are going to put the solutions. What is the the degree of dissociation conductivity is given? What is the relationship? Alpha is equal to lambda C by lambda naught. Only three parameters, two would be given and one would be asked. Here lambda C is given means asked is lambda 0 is given, should be given, it is given 400. The degree of dissociation should be given, it is 4.2%. But here the degree of dissociation should be in fraction. It should be in fraction. Therefore, convert into fraction 0.042. That is divided by 100 lambda C by lambda naught. Okay. You can easily, the lambda is equal to 400. Lambda C you have calculated. Next thing I am going to give you is lambda C is known means you can calculate the kappa of the solution. What is the kappa? The specific conductance of the acetic acid. Lambda C, this normality is given, that is equivalent to 0.001. It is centimeter square, therefore it is 1000 multiplied by 1000 by n, and the kappa can be calculated. This is the first one. Next, H plus ion concentration can be calculated. You may be asked to calculate what is the H plus ion concentration, for which what is the formula? C alpha. Therefore, I have derived this dilution formula. C alpha. C no, alpha is given. You can calculate the H plus ion. Knowing H plus ion, you can calculate, only you can calculate pH. pH is equal to, or now calculate what is C alpha. C alpha's concentration is 0.001. Alpha is equal to, sorry, 0.042. Therefore, multiply it by this, you will get 4.2 into 10 power 345, 10 power minus 5. What is the pH of the solution? pH is equal to minus log of the normality of the H plus. It is nothing but 4.2 into 10 power minus 5. Now log of A into B, staying it log of A minus log of 4.2. Log of this is 5 minus log of 4.2. You know the value of the 4.2, log 4 is equal to 0.6. 4.2 would be equal to 0.62, I think so. Therefore, the pH of the solution would be equal to 4.38. You may be asked to calculate pOH. pOH is equal to 14 minus 4.38. Is the only way. Any other things? Another thing is possible. Ka, what is the degree of dissociation of acetic acid? As per our formula, C alpha square by 1 minus alpha. We can now neglect the alpha. Why? Because the alpha is 0.042. If you subtract this, the value is 0.96. Therefore, neglect, you will get Ka is equal to C alpha square. C, 0.001. Alpha, 0.042. Square it. What is the value obtained? That is Ka. If Ka is obtained, you can calculate pKa. You may be asked to calculate pKa. Therefore, giving this data, what is the data? Lambda naught and C, and the degree of dissociation, you can calculate the kappa, the specific conductance. You can calculate the H plus ion. After finding the H plus ion, you can calculate pH. The third thing, if you are able to calculate pH, you can calculate pOH of the solution. The fourth thing. Then next, the degree of dissociation of the electrolyte can be calculated. And Ka is calculated, you can calculate pKa, the relationship minus log of Ka. Therefore, if this is given, you may be asked to calculate all the things. Work out one or two problems and you find it very easier for this. The problem I am going to give is a homework to you, just like this problem. Take down this problem. The lambda naught or lambda zero for ammonium chloride, for ammonium chloride, sodium hydroxide and sodium chloride are ammonium chloride, sodium hydroxide and sodium chloride are 230, 270 and 109 per ohm. per centimeter square per equivalent. For 0.01 normal sodium ammonium hydroxide, weak base ammonium hydroxide, equivalent conductance is 9.3. The equivalent conductance, they mean for this concentration, the equivalent is 9.33 per room centimeter square per equivalent. Here they have given the lambda naught for various strong electrolytes. Now, what are the problems that can be asked? These are the data given. What are the problems that can be asked? From this value, you can calculate the lambda naught of ammonium hydroxide. You can easily calculate. The last class we have worked out some example how to calculate the lambda naught of a weak electrolyte from the strong electrolyte. If you know this one and if you know this one, the first step you can calculate is what is the degree of ionization of ammonium hydroxide. First things. If you know the alpha, the degree of ionization, the next is you can calculate the kappa of the ammonium hydroxide. Or you can calculate the concentration of the OH minus using the formula C alpha. If OH minus concentration is calculated, you can convert into POH. If POH is, you can convert it into pH. Then you can calculate Kb. Kb is equal to C alpha square. Here we are omitting the alpha for the mathematical calculation, simplicity of the mathematical, because no calculator is given. But in the JAM examination, they will provide with you the virtual calculator. In that case, you can make use of this because they are expecting the answer truncating to 2 decimal. In such cases, you should not neglect alpha. But here we can neglect alpha because we are applying the approximation method. Therefore, C alpha square. Kb is known means Pkb can be calculated. Therefore, all these problems, any one problem may be asked to calculate. You work out in your home and you will be catching this concept. With this type of problem, I am going to move to the next type, that is ionic mobility. This application of Kohlraas law is over. Next is the ionic mobility. Here, the ionic mobility is abbreviated and parameter is given as capital U, or in some book they will put it as a mu. You are going to see the difference between ionic mobility and ionic speed or ionic velocity. What's the difference between ionic velocity and ionic mobility, and how this ionic mobility is determined, and what would be its application, determination of this ionic mobility lead to what? We will shortly see this one. First, we will see, let us take an electrolyte, any electrolyte, a strong electrolyte. When dissolved in the water, the ions present, the ionic solids are all separated, well separated, and there will be positive and negative ion, positive and negative ion, positive and negative ion, so on. Positive and negative ions. And in solution, you have studied that these ions are not at simply in the stagnant position, it is going on moving. And the movement of these ions, we call it as a random moving. It is not passing in a straight line, it is passing in a random, because during this movement, it will collide with the nearby ions. and hence its direction of the path would be changed. Therefore, undergoing, we call the directional changes as scattering. Okay, and what happened to the movement of the ions in this electrode? In this electrode, when you are introducing electrodes and apply the current, what happened? What happened to this? The positive ions, you are applying an potential to the electrode, and the positive ions, now let us assume this is the cathode, it is negatively charged, and it is the anode, it is positively charged. It is applying the positive potential, it is applying the negative potential, and the cations are all moving towards this electrode in a straight line. It is passing. The ions present in between the two electrons are moving towards the appropriate electrode, cations towards the cathode, and the anode towards the anode. Now we call this as a movement of these ions, or with what speed it is moving, that is, how many centimeters per second it has traveled in the applied potential. We call it as the speed of the ion, the centimeter traveled per second, or in some book in the SI units, they will give you the meter it has traveled when in the applied electric field. Without the electric field, you can't give the speed of the ion because it's undergoing frequent scattering. Okay, now I am applying, say, 90 volt across the electrodes. These ions, cations and anions would be having its own speed, 90 volt, under 90 volt. I'm going to increase the voltage, that is the potential difference to 100 volt. What about the speed of that ion? Whether it is remaining same or it will be increasing or decreasing, it is increased because attractive force is increased. Therefore, the speed is going on increasing. Therefore, what do you mean by this? The speed of an ion in an applied potential is potential dependent. What is the potential? What is the voltage you are applying? It is called, we are calling it as the speed. Therefore, what do you call or speed or velocity? Therefore, the speed of an ion is the distance covered by the ion per second in a applied medium, under an applied electric field. The speed of an ion is the distance covered by the ion per time. Here we are not mentioning what is the distance. It should be measured in meter or centimeter, and the time in per hour or per second. We have not mentioned per time in a medium under an applied electric field. That is very, very essential because only in the applied electric field it is moving directly towards this one. And this speed depends on the potential different applied on the electrode. Potential applied on the electrode. And the unit for this speed is either centimeter per second or meter per second. This is called the speed of the ion. But now we are going to define another parameter called ionic mobility. Here we are going to give the movement of the ions in an applied field, but that movement should be a constant value. Then only we can apply it for a constant conductivity for that ion. But we have seen that the speed of the ion is dependent on the voltage we applied it. Therefore, how to define the ionic mobility? And scientists has discovered a method to have a constant value for a particular ion, a constant speed for a particular ion. That is speed we call this as the ionic mobility. And what is the definition? The ionic mobility is defined as the distance traveled by an ion per second. Note here the time should be per second under a potential gradient of 1 volt, 1 volt per meter or 1 volt per centimeter. Therefore, there will be two unit. It will be simply written as 1 volt per centimeter or 1 volt per meter. This is the unit for potential gradient. What do you mean by potential gradient? First, we will see this potential gradient. The potential gradient is nothing but the potential difference between the two electrodes. What is the voltage difference between the two electrodes divided by the distance between the two electrodes. Potential difference between the two electrodes. Potential difference between the two electrodes and divided by the distance between the two electrodes. And the potential gradient would be having, now we are having two, according to this definition, two types of a unit. The potential difference between the two electrodes is given in terms of volt by the distance between the two electrodes. If you give it in the centimeter, now the potential gradient is given as volt per centimeter. If that is given in volt and distance between them is given in meter, it is volt per meter. Therefore, the potential gradient we have given here is the 2 unit volt per centimeter or volt per meter. Now, what is the definition for ionic mobility? The ionic mobility is defined as the distance traveled by an ion. The distance traveled by the ion is nothing but the speed of the ions. Let us have the speed of the ion. The speed of the ion per second, because they are defined as a per second, divided by the potential gradient. If you fix the potential, that is for 1 volt per 1 volt per meter or per centimeter, this ion speed is remain to be the constant. That we call it as the ionic mobility. Therefore, ionic mobility is defined as the speed of the ion in a medium under a potential gradient of 1 volt per centimeter. Whereas for the ionic velocity is the distance traveled by the ion in a medium under an applied electric field. They are not converting into a potential gradient. And what is the unit for this one? And that speed of the ion unit is so many centimeter per second we have given, or it may be given so many meter per second. That is speed of the ion per second, divided by potential gradient. The potential gradient is given as so many volt per centimeter or so many volt per meter. Therefore, what is the unit for this ionic mobility? Centimeter square per volt per second, or some books centimeter square per second per volt. What is the unit for this? Centimeter, I'm sorry, meter square per second per volt. This is the unit for ionic mobility. That is the unit for, that is centimeter per second or meter per second is the potential gradient. Therefore, U, that is plus, or U may be represented as U minus. U plus means the ionic mobility of the cation. U minus is the ionic mobility of the anion, is given by the speed of the cation by the voltage potential gradient. Potential gradient. And what is the definition for U minus? Speed of the anion by the potential gradient. Potential gradient. If the cation and anions are present under the same electric field, if the cation and anions are present in the same electric field, now U plus by U minus would be equal to what? The same field, U plus by U minus would be equal to what? Is equal to the speed of the cation by speed of the anion. Speed of the cation by speed of the anion. We call it as R, the ratio of the speed of the cation by speed of the anion. If the cation and anion are present in the same electrolytic shell, because the potential gradient would be same, they would be gets cancelled. You would be getting like this U plus by U minus the speed of the cation by speed of the anion. It is equal to R. And you keep it in mind, and then we are going to relate this ionic mobility to the ionic conductance. After seeing this relationship, we are going to work out some problem in this ionic mobility. And for this relationship, you keep it in mind. The U plus can be calculated or U minus can be calculated using the relationship, the speed of the cation divided by potential gradient will give you U plus. How to calculate potential gradient? I have already given this, the potential difference between the two electrodes divided by the distance between the two electrodes. Similarly, U minus can be calculated. Sometimes they would give you the ratio of the speed of the cation by speed of the anion, and you may be asked to calculate what is the U plus value, and they would give you U minus or vice versa. They may be asking this question, but these questions are all basic level. Now we are going to see the relationship between ionic mobility, that is U, and the ionic conductance. Ionic mobility and ionic conductance. Ionic mobility is represented as either U plus or minus, and ionic mobility, ionic conductance as lambda plus or minus, lambda plus or minus. And you'll put the equivalent conductance of a cation is directly proportional to, the conductance is directly proportional, is the mobility of the ion U plus. Similarly, lambda minus, the anionic conductance is directly proportional to the movement of the mobility of the minus ion. This is for one ion is moving at this speed, and equivalent conductance, if you ask to calculate, it is equal to the equivalent, that is the Faraday. One equivalent is nothing but 1 Faraday plus at infinite dilution. Therefore, lambda minus equivalent. If only one F is present, it is equivalent. F U minus dot. But if Z valency of the ion is Ez plus and Ez minus, the equivalent conductance may be calculated, converted into lambda naught, sorry, here put is not here also. Lambda naught, the molar conductance is equal to Ez plus into F U plus naught. If only one is given, only one charge is present, multiply it by you will get equivalent conductance. If the ion consists of Ez plus ion, It will give you, multiply this with this, you will get the molar conductance. And here also lambda 0 minus here plus minus equivalent and molar conductance is equal to Z minus into F into U minus naught. What is the total conductance at zero condition is equal to of any electrolyte is equal to sum of this and sum of this. F is constant, take it outside. Ez plus into U plus naught plus Ez minus charge over the anion and U minus naught, the ionic mobility of the anion. This is the general equation. And for 1:1 electrolyte, 1:1 electrolyte, or we can call it as the sodium chloride. Here the charge is +1 and -1. If you put the Z plus and this one, F is equal to the charge over is +1, therefore U plus naught and U minus naught. If you know the ionic mobility, you can calculate the lambda naught. If it is a zinc sulfate solution, you can calculate this. F is a constant, Z plus is 2 plus, Z minus 2 minus. You can calculate this one. Aluminum molar solubility, aluminum sulfate, and 2 into 3 plus. Here one ion consists of 6 plus charges. There was 6 into U plus, and sulfate ion thrice 3 into 2 minus 6. You put this, you will get the molar conductivity of aluminum sulfate and so on. This is the important application of this. And if you put for a single electron, 1:1 type of 1:1 univalent electrolyte, lambda plus at naught by lambda minus at naught is equal to F into U plus at naught divided by F into U minus naught. F and F cancel. Therefore, lambda plus naught by lambda minus naught is equal to ionic mobility of an ion cation by ionic mobility of the anion. This we have already called it as the ratio of the speed. Therefore, now this is equal to this. This relationship would be useful for you to calculate some other things. And now this ionic mobility can also be used to calculate this conductance of the whole electrolyte, or it can be useful to calculate the conductance, ionic conductance of either cation or the anion. Now we are going to see some problems under this. Then we will go for the transport number. We go for the transport number. Sorry. Take down the problem. At 18 degrees centigrade, at 18 degrees centigrade, the mobilities of ammonium and perchlorate ions, ammonium and perchlorate ions, the mobilities of ammonium and perchlorate ions are 6.6 into 10 power minus 4 and 5.7 into 10 power minus 4. It is given in centimeters square per second per volt, respectively, at infinite dilution. Calculate the equivalent conductance of ammonium perchlorate at infinite dilution. You can easily calculate it, for which we have given the formula lambda naught of ammonium perchlorate is equivalent to, what is the formula we have given? F into, and the charge over this ion NH4 plus and ClO4 is at plus only, U plus naught plus U minus naught. These values are given. This is no multiply. This you will get the per ohm centimeter square per equivalent. work out in your home. Take down the next somewhat difficulty, not difficulty, but we compare the previous problem. This to the ultimate one. For H in the sodium plus ion, the equivalent ionic conductance values, equivalent ionic conductance values at infinite dilutions are 350 and 50 per row centimeter square per equivalent per row. That is ionic conductance. They are giving lambda plus and lambda minus they are giving. Calculate the ionic mobilities. Calculate the ionic mobilities and ionic velocities. Calculate the ionic mobility and ionic velocities of these ions. Look here, ionic mobility they want, ionic velocities also want, they want. Present in a cell in which the electrodes are 5 centimeter apart and a potential difference of 2 volt is applied. 2 volt is applied. Once again, try and read the problem. First, what is given, what is asked. If you write down these two, immediately you can give this is the formula I have to apply. First of all, look here, they have given lambda naught of plus, lambda naught of minus. Okay. They asked ionic mobilities, U plus naught, U minus naught. They are asking these two. And ionic velocity of V plus, or velocity of plus and velocity of minus. They have given the electrodes are 5 centimeter apart from each other and 2 volt. And looking is given this and this that, and you can relate what is the equation to be used. Equivalent conductance and ionic mobilities. The plus is equal to F is equal for equivalent conductance, F into, and tell me, F into U of plus. Here they have given this one. They are asking this one. Is it possible for you to calculate this one? U plus can be calculated. Taking this by Faraday. Faraday, you know this. This is given as 350, put it here, 96,500 here. You will calculate this one. And the meter square per second per volt. This is for the U plus. Similarly, you can calculate U minus. Okay. You work out in the home, you can easily calculate U minus. Next question is asked is velocity of the ions. And velocity. Now you know the parameter, What is the relation between these two? You know, the U of any this is called speed of the cation. Plus means speed of cation. They are asking this one. Velocity means they are asking this one by potential gradient. Potential gradient. How to calculate the potential gradient? We have already given so the potential difference 2 volt divided by this one. What is this one? That distance between the two electrode 5. Therefore, this is you have to calculate, and this is you have already calculated. Now you can calculate this one. What is the unit for the speed of the cation? Here it is given in the centimeter. Definitely centimeter per second is the unit for this. From the U plus unit, you can calculate what would be the unit for the speed of the cation. That can be also worked out. This is another type of problem. Okay. And I am going to the third type of problem in this section, and then I will wind up this one. Then we will go for the transport number. Take down this question. A dilute aqueous solution of potassium chloride. A dilute aqueous solution of potassium chloride was placed between two electrodes 10 centimeter apart. If at all the distance between the two electrodes is given, you can boldly say the problem is the ionic mobility. The problem is the ionic mobility because no other problem. This distance between the two electrodes would be given. Continue the problem. A potential of 6 volt, a potential of 6 volt is applied. Calculate the distance traveled by K plus ion, the distance traveled by K plus ion in 2 hours. 2 hours at 25 degrees centigrade. If ionic conductance of K plus ion at infinite dilution is 73.52 per ohm centimeter square per equivalent. What is asked? Once again, these are what is asked. First, write down that one. What is the distance covered? They are asking distance covered by K plus ion in 2 hours. Okay. This can be calculated if you know the speed of the ion. The speed of the ion per second. Okay. If you calculate for the speed of the ion per second, the speed of the ion is related to ionic mobility. Okay, for which ionic this and potential difference gradient is required. They have already given this potential gradient. Therefore, from the ionic mobility, you can calculate this one. Ionic mobility is directly given or not? It is not at all given. Instead, they have given the equivalent conductance of the K plus ion. Is there any relationship between this ionic mobility and yes, lambda naught of K plus is equal to F into U of K, this one. Therefore, from this, you calculate this. From this ionic mobility, calculate the speed of the ions per second. From the speed of the ion per second, multiply with the 2 into 306, 3,600 seconds, that is 70,200 seconds traveled by the K plus ion. These are 3 steps process is there. I think you understand the problem. Therefore, you can work out this. Finally, find whether this type of answer is arrived at not. 3.3 centimeter is the answer. Here we are calculating in terms of centimeter because all of them are given in centimeter. We will calculate this. If at all it is asked in meter, finally you convert the centi in the place m should be placed and centi is equal to -2 meter. You can easily convert into the meter. Therefore, it's given in centimeter square. Work out in that and work out the final answer given. From that, you can also be immediately convert this one. Okay. Next, we will go to see the transport number. What is meant by transport number? The transport number mobility. Therefore, the ionic mobility, transport number, and the equivalent conductance are all related to each other. Therefore, I'm going to give the what is the relationship between them, and from that relationship and which parameters are given. Therefore, which relationship you have to pick out to work out the problem. If you keep that relationship in your mind, you can easily work out the problem in this section. Problem, which a relationship should be carried out to carry out this problem. That is essential in this type of uh, solving problems in this type of section. Transport number first. You're going to relate the transport number to the mobility. The mobility is already related to the equivalent conductance. Therefore, these are all related to each other. Transport number. It is represented by T, small t, for cation T plus, anion T minus. Another name is for the transference number. Transference number. Also, it is also called as Kitav's number. Kitav's number. Kitav is a scientist who calculated this transport number. Sir, what is maybe a transport number? Yes, we are going to see this shortly. And hence the number is also called by his name, Skitav's number. And whenever in the electrolyte, the cation anions are present here, you are applying voltage between two electrodes. The current is conducted by the cation and the anions. But the speed of the cation and the speed of the anions, whether they are same or different, they are different. Among the cations also, if you see the ionic mobility among the cations, the ionic mobilities are varying. What are the factors of, affecting the speed of this or the ionic mobility? The one thing is to what the charge density present over the cation is the deciding factor. What is meant by the charge density? You know the charge density is nothing but the charge over the cation by its size. Size is nothing but the volume, we will call it the radius of the ion. The charge by size is called the ionic density, a charge density. Higher the charge density, higher would be its hydration power. For example, if you compare the lithium ion, sodium ion, potassium ion, rubidium ion and cesium ion, which is having larger size. This cesium is larger and this is in a group, the size is going on increasing. You are studying this. Therefore, but the charge over in all of them is only one charge plus one, but the radius is going on increasing. Therefore, the charge density in the case of cesium ion is very small. One charge divided by the radius. Here, one charge divided by this radius, one charge divided by this radius. And the charge density over the lithium ion is very large. And whenever the charge density is large, the lithium ion charge density, the surrounding water molecules, the solvent molecules, here it is a positive charge and it is having negative charge and positive charge. There is force of attraction is higher and the ions are getting solvated. And how many number of solvent molecules should be surrounding around the ion? It depends upon the charge density. It depends upon charge density. Higher the charge density, higher would be the hydration. Therefore, you keep it in mind which ions would be easily hydrated, which ion would be having higher number of solvent around this. The lithium ion is having higher amount of charge and solvent around it. Whenever it is moving, it should also take these solvent molecules along with this. Therefore, the net weight is tremendously increased. Therefore, the speed of the lithium ion is found to be very, very less in this. Therefore, along a guru, the ionic mobility is going on increasing. If it is the case, what about the H plus ion you expect? It is the easiest, it should be easily undergoing hydration and it should be having the lowest ionic mobility we are expecting. But contrary to our expectation, it is the highest ionic mobility. And the lambda H plus ion is the highest one, nearly 350. And this conductivity is 350 per ohm centimeter square per equivalent. It is having the highest conductivity. Why there is a paradox in this? Go and refer, you will find it answer. So is the case with the OH minus ion. Among the anion, OH minus ion is having higher conductivity, but less than the H plus. But among the anion, it is having highest conductivity or mobility. Why? You can also find the same nearby same answer when you are going to try to find out answer for H plus ion. You will be coming across the answer for the OH minus ions also. Okay, with this introduction to ionic mobility, here ions are carrying the charge. Whether they are having and carrying the same current of same amount of electricity towards the cathode and anode. No. For example, zinc sulfate, the zinc ion and the sulfate ion. What about their conductivities? It depends upon the solvent molecules present among this. Whatever may be its size factor is also a deciding one for taking the water molecule. Therefore, their conductivity will be not equal. Having a slight higher conductivity. Another is having lower conductivity. But the full current would be conducted by the cations and anions. And depending upon their ionic mobility, the fraction of the current conducted by the cation and the fraction of the current conducted by the anion are different. That fraction of the current conducted by the cation is called the transference number of the cation, and the fraction of the current conducted by the anion is called the transferent number of the anion. And the transport number or transference number, sum of these two fraction would be definitely equal to the whole current conducted by these. Therefore, the amount of the current conducted by any ions depends upon three factors. One is the number of that ions present in the molecule, number of the ions present in the molecule. Second thing, the charge of that ions, whether it is having 1 plus charge or 2 plus charge or 3 plus charge, higher the charge, higher would be the amount of electricity that is passed, therefore charge of this ion. And the third is the mobility of the ions. What is the speed with which it is moving? Therefore, all these parameters, three parameters, is deciding what is the current conducted by cation is directly proportional to the current conducted is the number of the cations present in the molecule, n plus, into the charge of the each ion, Z plus, into the mobility of that ion, cation. Similarly, the current carried by the anion, is directly proportional to the number of anions present in the molecule, N minus, and the charge carried by each anion and its ionic mobility. But these two, when you add, that is equal to the sum of the current carried by these. Now, what the definition says? The fraction of the current carried by the cation is given by the current carried by the cation is this one, N plus into Z minus Z plus into U plus. This is the fraction carried, and this is the current carried by this. What is the total current? The current carried by the cation and the current carried by the anion plus N minus Z minus and U minus. This we call it as the transport number or transference number or Kirchhoff's number. For univalent electrolyte like sodium chloride, we simplify. This is the general equation for applicable for any electrolyte. For univalent electrolyte, sodium chloride, number of ions present, cation present in the molecule is 1. Therefore, N plus is equal to 1. The charge is 1. Therefore, U plus divided by, for the chloride ion 1 and the charge is also 1, you will get U plus plus U minus. This is the relation for the univalent electrolyte. And similarly for T minus, you can easily write the relationship U minus by U plus plus U minus. Therefore, if the ionic mobility is given, you can calculate the transport number and vice versa. And what would be the T plus by T minus? If you divide one by another, you will get U plus by U minus. U plus by U minus is nothing but R, the speed of the ratio of the speed. Therefore, this is equal to this is equal to this, and lambda plus by lambda minus is also equal to R. Therefore, if the speed ratio of the cation and anion is to be given, that can be related to the equivalent conductance of the ionic, the ionic mobilities, and the transport number. All these can be interrelated. And if the R is given, it is possible to calculate the T plus. It is possible to calculate the T minus, the speed of the ratio of the speed of the cations and anions are given. It is possible to calculate this. How is it possible? We are going to see this. And the T plus is equal to U plus by U plus plus U minus. Divided by U minus, you will get U plus by U minus divided by U plus by U minus plus 1. What is U plus by U minus? That is nothing but R. That is speed ratio by cation and anion. This is equal to R. That is equal to T plus. Therefore, if R is given, we can calculate the transport number. The speed ratio is given. Similarly, you can write out for the T minus in terms of R. And how to calculate? Number of methods are there, or you can make use of this method. T plus and T minus is equal to 1. Therefore, T minus is equal to 1 minus T plus. If you calculate the transport number of cation, subtract it from 1, you will get the transport number of the anion, and vice versa. Therefore, T plus and T minus, and 1 minus the T plus is given by R plus 1. And you put here R plus minus R by R plus 1. You will get 1 by R plus 1. Therefore, 1 by R plus 1 is the equation for this. This is another relationship. And also we have calculated the equivalent conductance for this one. What is this one? This T plus. Now we are going to relate T plus with respect to the ionic equivalent conductance. T plus is equal to U plus by U plus by U minus. We have given. Multiply both numerator and denominator by F. This is equivalent to what? that is equivalent to nothing but this is equivalent to what? This is, sorry, 0. Put it here, 0. Therefore, 0, 0, 0, 0. This is nothing but the lambda of the cation at infinite dilution. This is the lambda of the cation at infinite dilution. This is the equivalent conductance of the anion. This is equivalent to what? Lambda naught plus by the equivalent conductance of the electrolyte. Okay. And this can be calculated. Therefore, T plus can be calculated if the equivalent conductance of the ionic conductance at the infinite dilution and the equivalent conductance of the electrolytes given, T plus can be calculated. It is interrelated like this. And finally, T plus and this one. And okay, that's all about, I think so. And the last, on this one, last one. The lambda plus of this one is equal to T plus into lambda of the electrolyte from this relationship. Lambda, these two are given, T plus of this cation and electrolyte equivalent conductance. Similarly, lambda minus is equal to T minus into lambda of the electrolyte. Therefore, if you see this type of relationship, definitely anybody can be easily confused. And what is the relation I have to seek to solve this problem? Take down the ultimate relationship for univalent electrolyte. I am giving it for univalent electrolyte, and multivalent electrolyte I am not giving the relationship. T plus the transport number of the cation is equal to U plus U plus U minus. This is a 1 or it can be U plus by U minus by U plus by U minus plus 1. U plus by U minus is equal to R by R plus 1 equal to F into U plus 1 by U plus F into U plus U minus equal to the equivalent conductance of the cation by the equivalent conductance of the cation plus equivalent conductance of the anion is equal to equivalent conductance of this cation by the equivalent conductance of the electrolyte equal to what is, there is one more relationship that can be filled in after seeing the determination of the T plus by Hitaf's method. How to find out this one? After seeing this, we will fill up that gap. Therefore, which is asked and which relationship we have to make use of it, this one. That can be usually which is among this, I have not mentioned anything else. And there is a separate one. That is another separate one is T plus by T minus equal to U plus by U minus equal to lambda naught plus by lambda minus naught is equal to R. This is another relationship. Therefore, keep it in your mind. You can easily work out the problem without any confusion, which relation we have to make use of this. Here, if the T plus is calculated, you are asked to calculate T minus. That can be easily done. Okay, then keep this in mind. We will going to see that determination of the transport number by Hitaf's method. In Hitaf's method, we are having two conditions. What are the two conditions? The electrolytes is electrolyzed by One, the inert electrode platinum. If you use the inert electrode platinum, the problem is one type of problem. On the other hand, if you use a active electrode in the anode side, we have already said anode active electrode means from this electrode ions are released. This is minus, this is plus. That is, this is, for example, copper electrode. This is platinum electrode. This is the copper sulfate. In this case, also the heat-off number would be somewhat calculation is a slight difference is there. And carefully look out here. Before applying electricity, the cations and anions present around the cathode and anode and R will be the same. We are not applying any potential. Therefore, the cations and anions present around the cathode and anode would be remaining same. Now we have applied a potential. What happened? The plus values are moving towards the cathode. Why they are all moving towards the cathode? Because the cations present around the cathode would be getting deposited, taking the electron in the cathode and getting deposited. And due to the depletion of cation around the cathode and imbalance between this solution, in the anode side, cathode ion would be higher, and in the cathode side, it will be lower. Therefore, what happens? These cathodes are attracted, cations are attracted towards the cathode. Therefore, they are moving very fastly towards the cathode. If you are not disturbing the solution, ultimately, after stopping the electrolysis, ultimately you find around the cathode, around the anode, the concentration of cation would be less. Cation would be less. And how much would be less? It is equivalent to what is deposited on the cathode. What is deposited on the cathode. And you extend or you can parallel or you can extend the argument, this discussion to the anode also. And after electrolysis, in the cathode compartment, anions are depleted. Therefore, during after electrolysis over, around the anode, the cation concentration is decreased. Around the cathode, the anion concentration is decreased. As long as the electrolytic cell solution should not be disturbed, don't stir with any rod, etc. If you are stirring this, there will be a no depletion because immediately due to the concentration gradient, they would be getting uniformly mixed together. Therefore, to determine the transport number, you should not disturb the solution either in the anode side or in the cathode side, for which a method or a special designed apparatus has been designed by Kittabs, and you might have studied the determination of this one. And if you know this fact, you can calculate the cation transport number T plus. Here, that is nothing but the fraction of the current carried by the cation is called the transport number of the cation, or the current carried by cation. Current carried by cation while moving towards the cathode by the total current. This is the basic definition for this. And here, the current carried by the cation can be easily calculated. How? How much amount is deposited here? So many, and so much are deposited, cathodes are deposited at the cathode. That is equal to the concentration decrease around the anode. Therefore, instead of putting this current carried by the cation is directly proportional to the decrease in the concentration in anode compartment. How would you find out this one? Before starting the electrolysis, what is the current that is present? I'm sorry, what is the concentration that is present? And after stopping the electrolysis, now what is the concentration present around the anode? You can find the difference in the concentration. Put the decrease in concentration in the anode compound, which is directly proportional to the current carried by the cation, by the total current passed. How would you decide the total current passed? For which this apparatus is connected in series with the coulometer. Coulometer is a device, is also electrolytic cell, in which copper sulfate is be electrolyzed in series with that electrolytic cells, and which copper is deposited at the cathode, and find out how much amount of cathode is copper is deposited. So much amount of copper equivalent metal ion would be deposited in the cathode also. Therefore, here divided by the equivalent weight or number of equivalents of metal deposited in the coulometer. Metal deposited in the coulometer. That coulometer may be copper coulometer or silver coulometer. Here the cation you used is maybe a different. Therefore, here if different metal ions are used, you have to find the decrease in the concentration here, equivalent concentration. You should express the decrease in the equivalent concentration and equivalent of the metal deposited. If both the metal ions in the numerator and denominator are different. If they are all same, you can make use of the gram, decrease in the gram concentration, you can make use of it. Therefore, T plus is having another method. This is the experimental method. You put this relationship in that one and completely fill up this one. Now we are going to see another equation for the T plus when active electrode is used, like the copper sulfate and zinc sulfate. For this, the decrease in the concentration. If you find this during this electrolysis, from the original concentration, there is definitely a decrease in the concentration of the copper sulfate. But during the process, we have already seen this is active electrode. How much amount of copper would be deposited in the cathode? So much amount of copper will be released from the anode. Therefore, here the concentration of the anode is found to be, after experiment, found to be increased. Therefore, you have to give a correction why it is increased. The initial, let us assume that X is the initial concentration. And here in the process, X is the initial concentration. Y is the after the experiment is over. And Z amount of the equivalent is deposited at the coulometer, let us assume. Here the X value is higher, initial concentration, Y value would be lower because the electrode used here is the anode. Anode is a platinum electrode. Therefore, no metal will be exerted from this. Therefore, inert electrode, we put the initial concentration minus the final concentration divided by Z is equal to the equivalent weight of the metal deposited. But here, when you use the active electrode, here initial concentration is X. Once again, the final concentration is Y, and the coulometer Z amount of the metal is deposited. And since it is an elective electrode, copper electrode is an elective electrode, during the electrolysis, the Z amount of copper would be deposited, there increased. Therefore, you should sum of these X plus Z initial concentration and the concentration that would be increased during the electrolysis. Then you subtract, you will get the decrease in the concentration in the anode compartment divided by the coulometer reading. This is the main difference between in calculating the Itoff's number. You should find out whether the electrolysis parameter is given for the electrolysis of between the active electrode or between the inactive electrode. And we will work out one or two problem in this, and you will be having an idea over this. Take down this problem first. A solution of silver nitrate containing a solution of silver nitrate containing 12.14 gram of silver in 50 ml of anode solution. In 50 ml of anode solution was electrolyzed using platinum electrodes. Therefore, make whether it is between the inert electrode, notice it, or between active electrode using platinum electrode. After electrolysis, 50 ml of the anode solution was found to contain 11.55 gram of silver. Initial, it is 12.14 gram of silver. At the same time, 1.25 gram of silver was deposited in a silver coulometer. Calculate the transport number of ion. Transport number of ion mutta kataya kuduthirukanga. What is the transport number? They are asking for the T plus or T minus. The ion they are giving, they are previous lines they are giving, talking about the silver only. Therefore, they are asking and giving us T plus. Okay, whether we will be getting a T plus value or T minus value from the given data. T plus means there should be a decrease in the concentration in which compartment? Decrease in concentration in which compartment? Anode compartment. That is the compartment opposite to the cathode deposition, cation deposition by the total current. Okay, the total current is given by the coulometer study. Okay, if T minus, there will be a decrease in the concentration which compartment? Cathode compartment. Therefore, we'll look into the problem whether they have given a decrease in the concentration anode compartment or a cathode compartment. Then only making use of this parameter, we can calculate whether it is possible to calculate T plus ion, T plus of the ion, or T minus of the ion. Look out this, and what is given? Anode solution. There is a decrease in the concentration of the anode solution. Therefore, these parameters are suitable to calculate. And what I have told you that if the numerator, it is given the decrease in concentration in gram of silver, and the denominator, it is also given in the coulometer gram of silver. If both are in the numerator and denominator, same metals are there, And you can make use of the gram instead of the equivalent, because the gram should be converted into equivalent by dividing by 108. Here also you have to divide it by 108. 108, 108 gets cancelled. Therefore, you can directly make use of it. Instead, in the concentration given above is a silver, and they are making use of the copper coulometer. So many gram of copper coulometer is needed. You should not make it in the gram of the silver denominator, the gram of copper. You should convert into equivalent of silver by equivalent of copper. That is very, very essential. And this, to start with, we have given a simple problem. You can't, it is not necessary to convert the gram into equivalent. Now you can easily work out the problem. Decrease in the concentration of the anode. Initially, it is 12.14 gram, and after experiment, it is found to be 11.55. By the total current passed is obtained from the deposition at the cathode. Sometimes they may give the deposition of the cathode in the electrolyte, in the same electrolyte, or they may give it in the it's a copper coulometer, is so much amount is deposited. Anything may be given. Look at it here, it is given as 1.25. Here the grams of, here also grams. Here is grams of silver, grams of silver. Therefore, no necessity of converting into the equivalent. Just to make use of this, you can find out this one. If T plus is asked, you are calculating the T plus directly. And if you are asked to calculate T minus, subtract the T plus from T minus. Okay, so I think you follow this one. And they complete the problem after the session. Take down the next question. Take down the next question. A dilute solution of silver nitrate was electrolyzed. A dilute solution of silver nitrate was electrolyzed using platinum electrodes. After passing small amount of current for 3 hours, after passing small amount of current for 3 hours, a decrease of 0.00064 gram equivalent of electrolyte, gram equivalent of the electrolyte occurred in the anodic compartment. Occurred in the anodic compartment. The weight of silver deposited is found to be 0.54 gram. 0.54 gram. Calculate the T minus transport number of the anion. Calculate the transport number of the anion. Here, from the given data, you can calculate the T plus, because the anodic concentration decrease is given, is not. Therefore, T plus, it is given directly, so many gram equivalent has been decreased, gram equivalent. That is very essential. But in the weight of silver deposit is 0.54 gram. Here gram equivalent. Here also silver nitrate down. Here also silver is deposited. Silver nitrate means silver so many gram equivalent, nitrate so many equivalent. But we can't use this here gram equivalent, here it is gram. Therefore, you should convert this gram into gram equivalent by divided by 108. Then only you will be getting the correct answer. Okay. Therefore, when will you divide it by 108? Convert into equivalent when it is not necessary. Please keep it in your mind. Okay, take down the next problem. In an electrolysis of copper sulfate using copper electrode, underline this one, it's an active electrode, 0.135, 0.135 gram of copper is deposited at cathode. Okay, this is the total current. Okay, the weight of copper present in unit volume of anode solution, in unit volume of anode solution, before and after electrolysis, before and after electrolysis is 0.79 and 0.91 gram respectively. Here look at the concentration. Initial concentration is 0.79. Finally is 0.91. There is an increase in concentration. Itself you can easily say that due to ring electrolysis, when a copper ion is released, how much ion would be released? What is the amount deposited at the cathode? So much amount would be increased. Therefore, you should sum up these two, then subtract this one. You will get the deposit. No. Okay, you can also work out for this. Find out the T minus. Find out the T minus. Here, whether we can keep it in the gram itself or gram equivalent, you have to convert this gram equivalent, find out the, read the problem. Here so many gram of copper, here also gram of copper, gram of copper. Therefore, I think it is not necessary to convert into gram equivalent. You making use of this gram itself. Okay. Then we will see the another type of problem, making use of that gram equivalent, etc. Take down the problem. Take down the problem. Let's take down the problem. A solution of hydrochloric acid was electrolyzed in a cell between two platinum electrodes. Between two platinum electrodes. The cathode compartment contained make a note of it, cathode compartment contained 0.354 gram of chloride before electrolysis and 0.327 gram of chloride after electrolysis. A silver coulometer in series had a deposit of 0.532 gram of silver. Calculate the T of Ag plus, T of H plus, T of H plus. Here from the given parameter, which transport number can be calculated, T plus or T minus? Look into the given parameters. The cathode compartment concentration they are furnishing. Therefore, for the cathode means you can calculate only the T minus from the given parameter. That is difference in the concentration. Difference in concentration in cathode compartment divided by the total current. Total current. Okay, difference in concentration of the cathode, they have given before and after 3.54 minus 3.27 gram of chloride divided by the total current passed is given by 0.532 gram of silver. Here you should not carry the problem, solving the problem, having a gram of chloride and having gram of silver. You should convert into the equivalent weight. And this gram of chloride equivalent weight, what is the gram equivalent weight of how making use, how do you convert the gram of the chloride into equivalent and a gram of this into equivalent? How do you convert? Tell me. Divided by the atomic weight, because it is having the plus charge only. Atomic weight is the divided by the valence is the equivalent weight. 108 is that you have to divide it this one. And chlorine atomic weight is 35.5. Charge is also 1 minus, therefore equivalent weight is 35.5. Divided by 35.5, you can calculate the T minus. But what is asked? T of H plus is asked. Therefore, subtract the T minus from 1, you will get this one. Okay. And with this type of problem, I wind up this hit of numbers. There is also another moving boundary method. I find no times to complete that moving boundary method, and also that limiting law, Dalton-Debye limiting law, that is a log of activity coefficient is equal to 0.51 into Z plus or Z1 and Z2 into root of I, the ionic strength. Here, what is the ionic strength? Calculate ionic strength and calculate this activity coefficient, etc. Problems would be asked, but I find no time to calculate this. First, the ultimate, we go see the conductometric titration. And in the conductometric titration, we will give graphical representation. And this graphical representation from this, how the some question may be asked from this one. The principle of this titration, conductometric titration, from the name itself, here we are going to estimate a given solution by measuring the conductivity of the solutions at various concentration. We are going to conduct it. And as which ions are present in the beaker or in the reactive cells you have taken, the conductivity cell you are taking, and which ions you are going to add during the titration, and what happened to the conductivity, whether it is going on decreasing as the solid titrant is added to the titrant. You know what is the titrant and titrant? I think you know this. The solution taken in the conductivity cell is called the titrant. And the solution you are adding from the burette is called titrant. Therefore, which titrant is present here? Which nature of the titrant? What about its original conductivity? And which ion you are going to add as a titrant? Whether the addition of this titrant would increase the conductivity of the solution in the conductivity cell. If you understand this, the nature of the graph can be easily given. And what are the types of the conductometry titration they are carrying out? Generally, the acid-base titrations. The acid-base titration means the acid is furnishing H plus ion and the base is OH minus ion. Of these two, the conductivity of H plus ion is extremely larger because it is the first one stood first in the conductivity tabulation, the H plus ion. Though it is charge density is higher, it stands first. Why? For which you seek the help from the book. Okay, here what are the types of acid and bases we are going to use? A strong acid and a strong base. For example, hydrochloric acid versus sodium hydroxide or potassium hydroxide. And you are taking in the, which is to be added, we are taking HCl in as the titrant, and the titrant is sodium hydroxide. Here we are calculating the conductivity of the solution, and this is the volume of the base added. HCl you have taken, and as titrant is the base added. Initially zero concentration, the volume of the base added 1, 2, 3 or 10, etc. What happened? Here HCl is completely ionized as H plus and Cl minus. The conductivity of the H plus ion is very high in the present amount of H plus ion present in the conductivity cell is high. Therefore, even before adding the base, the conductivity of the HCl is higher. Then you are adding the titrant sodium hydroxide. What happened? And you add this one, it will be forming the OH minus would be snatching some H plus ion and water is present. In addition to this, Cl minus and Na plus is present. Here some amount of H plus ion is snatched. In the place, sodium ion is increased. The loss is higher, but a slight gain in the conductivity by the furnished by the sodium ion. It is a slight, but net is a loss in the conductivity. Therefore, when you add the sodium hydroxide, the conductivity of the solution is going on decreasing. Okay, it is decreasing. Up to what point? At the equivalence point. At the equivalence point, the sodium hydroxide is equivalent to added sodium hydroxide equivalent to the amount of HCl present. After at the equivalence point, only water, the chloride ion formed and sodium chloride ion is present or present. Therefore, its conductivity would be somewhat its conductivity. After that, every addition of the sodium hydroxide will furnish further amount of sodium ion and further amount of OH minus ion. You know, the OH minus ion concentration, its conductivity is high. Therefore, after the equivalence point, the conductivity is going on increasing. And the point of intersection, we call it as the equivalence point. From the volume of the base, you are adding this one. Okay. But now we are going to change this. Instead of strong base, we are adding a weak base. What happened to this? Here, once again, we are taking acid in this and base as the titrant. Volume of ammonium hydroxide we are using. Initially, hydrochloric acid is present. Therefore, conductivity before adding the sodium hydroxide would be higher. The conductivity would be during this reaction, instead of sodium hydroxide, we are using ammonium hydroxide. Here, instead of the sodium ion, which ion would be there? Ammonium ion would be there. Here, ammonium ion concentration is increasing. At the same time, H plus ion concentration is decreasing. If you compare the conductivity of H plus ion and ammonium ion conductivity is less, but it is slightly increased. H plus ion conductivity is larger. Net is the decrease in the concentration. Conductivity is very fastly. until the equivalence point is reached. Okay, after the equivalence point, what happened? You are adding ammonium hydroxide. This ammonium hydroxide is a weak electrolyte. Therefore, whether it is undergoing ionization or not, after the equivalence point, it won't undergo ionization. Why? Because already ammonium ion is present in the solution equivalent to H plus ion, because H plus ions are replaced by ammonium ion up to the equivalence point. In presence of such a ammonium ion concentration, since it is a weak electrolyte, we can say that no more uptake, no more ionization of ammonium hydroxide. Therefore, OH minus ion concentration would not be there, zero. Therefore, after this equivalence point, the conductivity would be remaining the constant. And this point of intersection, we call it as the equivalence point. Why it is not? Due to the common ion of the ammonium ion. But at the same time, if you see the reverse addition, reverse the addition. What is the reverse addition? The conductivity. You are taking ammonium hydroxide in the beaker. Ammonium hydroxide in the beaker. You are adding hydrochloric acid from the burette. What happened? Initially, ammonium ion, a small amount of ammonium ion and OH minus ion would be present initially, because a very small ionization. In that small ionization, it will be present like this. Okay. The OH concentration and ammonium ion is small, therefore conductivity would be very, very low. Now you are adding H plus hydrochloric acid. When you add hydrochloric acid, it will H and OH will be converted into water and the chloride would be replacing. Therefore, compare the OH conductivity and the Cl minus conductivity. OH conductivity is higher and the Cl minus conductivity is lower. Therefore, initially, a slight decrease in the conductivity. Then afterwards, the conductivity is going on increasing up to equivalence point, because more amount of Cl minus are blazing. Then after that, after complete equivalence point, H plus ion concentration in the solution is increased, in conductivity is higher, therefore a tremendous increase. Here it is not the equivalence point, it is a slight different decrease in the OH concentration initially, and this is the equivalence point. Therefore, a slight difference in the conductivity diagram, conductivity curves, and you should know this type of one. Similarly, you can expect the acid versus strong base. Here we have seen the strong acid versus weak base. Base is strong and acid is weak. Once again, two types of the curves. One is you can take the base in the, you can take the base in the, base as the, I'm sorry, what is called as the titrant from the burette. And you are taking the acid. Example is the acetic acid versus sodium hydroxide. The acetic acid is also a weak electrolyte. Therefore, the H plus ion concentration initially present is low, therefore low conductivity, and initially a decrease in the conductivity, then increase, sorry, a decrease in the conductivity, then increase. After the equivalence point, addition of the sodium hydroxide, there is a higher conductivity. It is equivalent to this type. This and this would be more or less the same. And if you reverse this, that is, you are taking the base in the conductivity shell and the acid is added from the burette, you will get a different graph. What is the graph obtained? That is a lambda. You are taking volume of acid, acetic acid added, weak acid, but a strong base is taken. Therefore, initially higher one, and it's going on this one. After the equivalence point, the weak acid cannot be ionized because during the reaction, sodium hydroxide and acetic acid already reacted to give sodium ion, and acetate ion is present in large amount plus water. Due to the presence of the common ion, acetate ion, it will not be after adding the conductivity will be remaining same. Similarly, you can go for the weak acid versus weak base. What is the nature of the curve? You can also give the nature of the curve obtained for the mixture of strong acid and a weak acid with a strong base. With a strong base. In this type, you will get two n equivalence point, volume of the base, and the first equivalence point is due to the equivalence point obtained by the loss of, for example, hydrochloric acid and acetic acids are present versus sodium hydroxide. This is obtained first like this. Then after a complete reaction of the HCl, now acetic acid will then be undergoing reaction with a slight increase. After complete is going to be increased. This neutralization point is due to up to this for HCl, and between this is due to the acetic acid, and this is the sodium hydroxide form. When you plot the silver nitrate and KCl, let us assume KCl is added. What is the volume of KCl added? What happened to the nature of this? Here, silver nitrate concentration is going on, decreasing, getting silver chloride precipitate would be obtained and so on. Okay. And silver volume of silver nitrate. Initially, the silver nitrate would be precipitated as potassium chloride. Silver chloride is precipitated. In the place of silver is replaced by potassium ion, potassium nitrate. Its conductivity of potassium ion is more or less to equivalent to silver. Therefore, conductivity is remaining constant. After all, silver nitrate would be precipitated as silver chloride. Now, KCl concentration is increased. Therefore, it is going on increasing like this. This is the precipitation titration. Here, one important thing is, but so far this question is not asked, or if at all asked, how to change the, how to give the diagram. Here, we have so far drawing one thing to say, we will take a weak acid and a weak base titration curve. Weak acid and weak base titration, taking the conductivity in the y-axis, conductance in the y-axis, and the volume of base added in the x-axis, volume of the base added in the x-axis. Here acetic acid and the weak base is say ammonium hydroxide. Let us take this one ammonium hydroxide. What would be happened to this? Here the acid is present H plus ion, its concentration is say like this. It is initially it is slowly replaced by the OH minus it is combining to give water, and then it is going on increasing. After complete neutralization, what are the ions present? Acetate ion, ammonium ion are all present. After in that ion, if you after the equivalence point, if you add ammonium hydroxide, whether it undergoes ionization or not, Definitely it is not undergoing ionization. Therefore, it is remaining constant. This is the nature of the curve obtained once WA, weak acid versus weak base. Now, one question, what is the question is, if the titration curve is plotted between volume of base added versus the conductivity. Note the change here. Here, x-axis, you are an volume of the base added. In the y-axis, the conductivity. And they want to give the volume of the base added in the y-axis and the conductivity in the x-axis. What would be the nature of the curve of time? I think so far this type of problem is not asked. If at all asked, how to give this? It's just invert the axis. How to invert the axis? Which you have to invert the image as a mirror plane. You have studied. Therefore, draw a mirror like this. This is a mirror. Or you can draw a mirror in this side also. Whatever the side draw the mirror first. You will take this in this side and how you would get the curve. And now the image obtained is like this. Here, volume of the base added. And the arrow will be just like this. Okay. And this lambda. The lambda is like this. And the arrow would be in this way. Okay. And the graph would be, instead of this, here it would be looking like this. It would be increasing. Then it is increasing in this way. Here it is decreasing in this way. Then it is remaining constant. Therefore, it is remaining constant. Okay. Now we have drawn the mirror images. And what to do? You have to invert the image in the anti-clockwise. For this, you have to invert in the anti-clockwise or rotate your notebook in the anti-clockwise and you will find this is the nature of the curve of time if the axes are changed. The axes are changed. Okay. This is the way you can draw any of the titration curve, but this type of curve is not so far asked. If at all asked, you can easily change this one. Or you can also draw this, here also you can draw the curve like this. Here, for this you have to invert this node by the clockwise direction. That's the difference. I think it will be easier for you. Therefore, making use of this, you can change the nature of the curve if at all asked. Okay. Therefore, what I have left in the electrochemistry is the Defay-Heckel limiting law, the moving boundary method. Using the moving boundary method, you can calculate the uh, transference number. And some more problems in the T plus versus the conductivity or the ionic problems I have not given, but I have given the relationship. You can make use of this. And thank you very much. Is there any doubt to anybody else? And I wish you all, dear participants, I wish you all to cross the energy barrier for clearing the competitive examinations like JRF or the GATE or the BARC examinations or any competitive examination. For I wish you all to cross the energy barrier. Okay. Thank you very much.